Okay, everyone, we started off with alcohols reviewing substitution reactions. So we have SN1 or SN2, and usually you can tell based on how substituted the alcohol is. This is a tertiary alcohol, so most likely it's going to go through some kind of carbocation intermediate when the leaving group leaves. So I'm going to try to get rid of this OH group and then put an halide nucleophile on there. All right, so how do I make this OH group leave? So we know hydroxide is a very bad leaving group because it's a strong base. It's not just going to readily leave the molecule. So in order to make this leave, I need to have protonation first. So first, I'm going to change that into water. And I'm going to get this intermediate, which then will leave and form my carbocation, which is planar. And then I've got my halide ion ready to attack it. So this is an example of SN1 because it goes through a carbocation intermediate. Now this reaction here looks like we should be able to do the same thing, right? Here's my water that gets formed. Now I have a good leaving group. This can take off. And then I could have chloride attack here. Now what's wrong with this mechanism? You guys see what's wrong with this? What's wrong with this is that this carbocation is primary. So this is not good, okay? Because it's very high energy primary carbocations compared to tertiary. So it's better for us to avoid a primary carbocation. So in this case, the better mechanism, I'll do in a different color, it would be to use chloride as our nucleophile that's going to attack and release the water at the same time. So once we do that, then I don't need to go through this. I can go directly to that. So this is our SN2 mechanism, which is concerted. Nucleophile attacks as the leaving group leaves, all in one step. Now another way to do this reaction that's very effective is to change the OH group into a different leaving group like a halogen or resonance stabilized tosylate ion. So tosylate, let me draw that out for you. TS is for tosylate. It's toluene sulfonic acid. It's an ester of that. So instead of an OH here, which makes it a sulfonic acid, it's an O group. Okay, so here's a CH3, and a benzene is tosyl or toluene sulfonate. Okay, so sulfonate, and this O is usually attached to something, an R group. So that's what this is, the OTS right here. So this whole thing is OTS. All right, now this is a good leaving group because when this O leaves, it's resonance stabilized with the sulfonyl group right here. So if I can convert it to OTS, all I need to do is react it with toluene, this toluene group here. This is a toluene sulfonyl chloride, okay? So I'm going to, technically the electrons flow upward and then there's an intermediate that then collapses and the Cl group gets expelled. So there's this reaction where basically you're substituting here. So Cl goes away and this O attaches and this gets deprotonated. So now this carbon is a lot easier to attack because now I can lose this group. So my nucleophile can come in and then my leaving group leaves. So this is still an SN2 type reaction. You can tell from the stereochemistry. So I have a wedge going to a dash, I have inversion. All right, so let's write that down as one of your alcohol reactions, okay? So that's a new one for you, is how to change the OH group into a different kind of leaving group. Rather than water, which we've seen before, you can change it to OTS. Now let's also keep in mind we can change it to a halogen, which is also a good leaving group. So there are two halides that we tend to use, chlorides and bromides, which are both good leaving groups. So the first one is to use something called SOCL or SOCl2. It looks like this. And this PY or pyridine is the solvent, and that looks like a benzene ring but with a nitrogen in it. So that's pyridine. And that's used as a base, but it's not nucleophilic because of the ring. So you don't want the nucleophile to, you don't want this to attack. You just want it to pick up hydrogens. Here, this is also done in pyridine, and this is PBr3, and what that does is it adds the bromine there. So those are the reagents we need for each of those. You do need to know the mechanism for these, so let's go through that. So the first step is we are going to consider, this is sort of like a carbonyl, right? We've got our partial positive, partial negative. So this is going to come in and attack here. And then after we attack there, because we have good leaving groups here, we're going to come back down. This is called a tetrahedral intermediate. This was planar, and now it's tetrahedral, but it's pretty unstable because of the charges there. So this is going to take off, and so we're going to end up with this intermediate now. So after that step, I end up with this, and now I need to deprotonate this hydrogen. So that's what the pyridine's for. It's basic due to the nitrogen's lone pair, and you don't have to draw the structure of this, but you do need to know what pyridine does. Grabs this H, and then the electrons go to the O there. Then I also have this chloride that came off, which is right here. Now what we're set up for doing is to replace this big group here, which if you notice, it's going to be resonance stabilized. This group gets attacked by the chloride that came off, because chloride is a good leaving group, but it's also a good nucleophile. Now at this stage, I'm going to release this bond. I'm going to break this bond and either put the electrons on the O, or I can just go for it and just show you how that all collapses into several arrows. I'll show you that first, and then you can decide for yourself how many steps you want to show. This can, instead of going on the O, it can go toward the S, and then these can go up, and then you'll have the tetrahedral intermediate again, which then can come back down and get rid of the other Cl. Or you can show these electrons going to the O, and then show the subsequent steps that way. Let me just show it this way for now. I'm going to show that the Cl came in, attacking here. This bond breaks, so now we have our chloride. So this chloride replaced this OH group. The rest of this stuff right here turns into SO2. You can see the SO2 forming here. But I'm showing this in steps. I'm showing this going like that, and then this can come down and expel that, ultimately giving me SO2 and Cl minus. And then you have protonated pyridine as well, which you don't have to draw, but I'm just going to draw it for fun. So pyridine chloride and SO2 are byproducts of this reaction. Our main reaction, though, is alcohols turning into alkyl halides. So this is one mechanism you should know. It seems pretty complicated, but just remember the first step is just attacking the SOCl2, SOCl, and then collapsing it, getting rid of a Cl, which then comes back and displaces this group. So you just show that breaking apart is a little bit complicated, but it ends up in the more stable products, which are SO2 and chloride ion. Now for PBr3, I've used up all my space. I have no room to show you this mechanism, so let me draw it out here. PBr3 looks like this. And this mechanism is very similar to SOCl mechanism, which I just showed you. Basically, the alcohol is the nucleophile. It's going to attack the PBr3 and let go of one of these Brs. So what we'll get is an O with our H as well as a PBr2, and then we have bromide ion that came off. Now guess what? Bromide ion, what do you think is going to happen with this bromide ion? Well, we saw when chloride came off, it came back and attacked and released this because this is a good leaving group because it'll make stable products here. So same thing here. This is a pretty good leaving group, so I'm going to use that and attack right here. And again, you could just like above, if you use pyridine, you could take this H off. It'll make this O more nucleophilic to attack here. Sometimes you see pyridine here as well. But in this case, this can leave by itself. So this comes back, attacks. That's how we get the bromide on there. And then this guy you can just show as a byproduct. All right, and now that we've done that, I'll also add the byproducts up here. You don't have to do it, but sometimes people wonder, whatever happened to the other stuff? So please know those two mechanisms. You could be asked about one of those two. Okay, so notice the stereochemistry though. For these reactions, it's all backside attack. So this is OH was in the front. When you tosylate it, it's still in the front. It's not until the nucleophile attacks that you have the inversion. For these, same thing, the OH group is, let's say if it was chiral, the Socal addition or the PBr3 addition is on the same side as wherever the OH group is. It's not until the attack that you have the opposite. So all of these reactions will result in inversion. These don't show it because this is achiral. Now remember, that's our way of converting our primary alcohols or secondary alcohols into good leaving groups. So here's our secondary alcohol. Instead of using acid and HBr, we don't want to have a secondary carbocation. So let's just go with our method of bromination here that we learned right here. So making an alkyl halide from an alcohol, if it's a bromide, use PBr3, and then that also explains why there's inversion. For this case here, notice this is tertiary, so do we need to use PBr3 here? The answer is no. You can get a carbocation and use acid to do that, and then have bromide attack and release, attack the carbocation once the water leaves. Okay, so this is just our SN1 reaction. In this case, you guys see that there's retention of the methyl group stereochemistry, but the hydroxyl and the chloride are inverted. So that means, again, I'm going to double check to see this is secondary. So I do want to change the OH to a better leaving group. So in this case, because I want Cl, I'm going to change this to Socal in pyridine. All right, so on your own, go ahead and finish these up. And let's move on to talking about elimination now. Elimination is where we converted the OH group to a better leaving group, but we used some heat, and we didn't want to use water because we don't want to add to the double bond and go backwards. So we use concentrated H2SO4, which means there's very little water in solution. This is also called dehydration because you're losing water, so you're dehydrating. So in this case then, I'm going to protonate this, and then using heat, so I'm going to have elimination favored when I have heat. This is going to leave, because this is tertiary, I can have a tertiary carbocation and then elimination this way, like that. So this is actually considered E1 because I don't have a strong base in solution. It doesn't all happen at the same time. It's in steps. So first the protonation, second leaving group leaves, third carbocation gets attacked, so the carbocation intermediate. So that's a unimolecular reaction. Here we have the reaction from before that we just learned, which is tosylation. And then after we tosylate this, now this is a good leaving group. I have a strong base, ethoxide. It's like hydroxide but with an ethyl group. This base is not going to wait for this group to leave. It's strong. It's going to come in and grab an H, and that's going to kick off this leaving group in a concerted mechanism. So this is E2 bimolecular. And you can add heat if you like to make it eliminate faster or to minimize substitution products. So let's practice with those two reactions. One of these is E1 and one of these is E2. Go ahead and give that a try. Tell me what the products are. All right, guys, we're back, and I think you noticed the first one is exactly like the E1 we did. Second one's the E2 we did. So with the E1, we're turning this into a good leaving group water using strong acid, and then a base in solution can, maybe a little bit of water in solution, can take this hydrogen off, and we can eliminate Zaitsev. The only thing to watch out for is multiple beta hydrogens. We have these beta hydrogens. We also have these beta hydrogens here. So you just have to be careful because they'll give you a different product with the double bond here instead of here. But we normally go with Zaitsev because that is going to be more stable than the Hofmann thermodynamically. That means the activation energy will be lower to make the Zaitsev product, so it'll be faster. But you will probably get both, so you'll get a major and a minor product, and Zaitsev will be your major product when you have E1. Now for E2, first we need to make a good leaving group. Instead of making water, we're going to tosylate. So this is a good leaving group here. Now we have multiple beta hydrogens, but they're all equivalent to each other. They're going to give me the same product. So that's what this does, is a strong base grabs one of these 4 beta hydrogens, doesn't matter which. Usually, if there was stereochemistry, though, it would matter. So like if, let's say this problem was changed to give you a wedge here, give you a wedgie. All right, so here's the wedge. And then we take the TS, and OTS makes this, and this is still going to be wedged. But now if I have a choice, this is E2, and some of you might remember the term antiperiplanar. So that just means that it takes the hydrogen that's anti to the leaving group. So if you had a choice, it would be the anti one. It still doesn't really matter, though. It's still going to give you this product, but just good to review those fine details and mechanistic points. Okay, so recap this video, okay guys, on a sheet of paper. Write out your E1, your E2, what are the reagents you need, write out your halogenation here, your alkyl halide from an alcohol reactions using these 2 reagents, and write out the mechanism for those in your mechanism portfolio. And then I forgot to mention it, but do the same for the previous videos. You've got Greenyard, hydride, you've got your SN1, SN2. Do all of that for your alcohols and make a map, reaction map of your alcohol reactions, or add it to previous reaction maps. Anything you can do to organize these ideas is going to help you remember them better and study them more clearly when it comes time to take the test. Okay, good luck.